It was made possible for humans to travel from Earth to the Moon by Newton's superior grasp of gravity. Have you ever wondered if our comprehension of time is only the top of the temporal iceberg, lost in the ticking of the clocks? Turned on its head, his discovery is more than a theory. It's a key that may open doors to the cosmos mysteries and reveal a universe more magnificent and complex than we could have ever dreamed. What are the ways in which Brian Cox's novel theory defies our conventional conception of time, and how can this affect the way we see the world? As we look into Brian Cox's recently published revolutionary hypothesis on the nature of time in the vast cosmos around us, join us on an exciting journey through the annals of time itself. There are mysteries to be solved, and among them are ones that have to do with time and gravity, two fundamental aspects of life as we know it. Imagine a universe in which time exhibits odd behavior, such as slowing down or accelerating. Furthermore, the force holding us to the Earth may not be what it first appears to be. This is the area covered by Albert Einstein's theories of relativity, where time and gravity become strange concepts to us. The famous scientist Albert Einstein gave us a fresh perspective on the cosmos with his theories of relativity. His research established the groundwork for our current understanding of time's behavior under various conditions, particularly when it is moving quickly. The special theory of relativity and the general theory of relativity, two groundbreaking theories put out by Einstein at the beginning of the 20th century, marked the beginning of it all. After its publication in 1905, the special theory of relativity revolutionized our knowledge of space and time. Put simply, it teaches us that regardless of an observer's motion, the rules of physics apply to all of them as long as they are not accelerating. Relativistic effects are introduced by this theory, which includes the well-known idea that time can slow down or dilate under specific circumstances. The light clock is an intriguing thought experiment that explains time dilation. Consider yourself inside a spacecraft traveling at nearly the speed of light. A light beam that is perpendicular to the direction of motion is bouncing between two mirrors within the spaceship. Since light travels at the same speed to all observers according to the principles of physics, the light beam must appear to move along a longer diagonal route. For the observer outside the spaceship and the one within, the time it takes for the light beam to follow its journey should be the same. It appears that it would take longer for the light to finish its journey, though, since the path appears longer to an outside observer. Time dilation is the term Einstein used to describe this apparent time gap between the two observers. When compared to a stationary observer, time slows down for the moving observer. Depending on your mobility, time works differently in this case. Relativistic effects, which describe how objects change with speed, are not merely theoretical concepts. Particle accelerators, such as the Large Hadron Collider, are massive devices used by physicists to accelerate particles to nearly the speed of light. Things move so quickly that precise measurements and forecasts require a new way of thinking about time. The special theory of relativity, which was developed by Albert Einstein in 1905, fundamentally altered our understanding of the cosmos, particularly with regard to time and motion. This theory contradicts what our instincts could tell us. It asserts that, regardless of their state of motion, everything is subject to the same set of physical laws. This is not like what we often experience, where we could assume that something moves quicker if we give it more speed while it is already moving. However, according to Einstein's theory, nothing can travel faster than the speed of light as a maximum. According to this frame of thought, someone traveling at almost the speed of light might not see events as happening at the same time that they do. Length contraction, which states that while something is moving, it seems shorter in the direction it is traveling when viewed from a fixed position, is another idea derived from this unique perspective. Then there's the well-known formula E equals mc squared, which illustrates how mass and energy may transform into one another. This has important implications for our knowledge of the behavior of ultra-fast particles, as well as for nuclear reaction dynamics and the splitting of atoms. Special relativity is applied in common technology such as GPS, therefore it's not simply a fancy theory. GPS satellites are in motion when they transmit signals to your device, and this mobility causes time to behave differently for them. Your navigation would be extremely inaccurate if we didn't account for this time dilation impact in our GPS computations. Therefore, time isn't the same for everything and everywhere. Rather, it varies on how things are moving, as special relativity informs us. This concept goes against how we often conceptualize space and time. It's similar to suggesting that our typical conception of the universe is a little incorrect. The special theory of relativity states that motion affects time rather than time being fixed. Numerous tests have demonstrated the validity of some fundamental concepts, such as the constancy of the speed of light and the relationship between mass and energy. However, there's more. Let us now introduce Albert Einstein's 1915 general theory of relativity. This hypothesis explores the intricate connection between gravity and the construction of the cosmos. It challenges the conventional wisdom that gravity is merely a force that attracts objects at a distance. Rather, it indicates that gravity results from the curvature or bend of space and time. According to Brian's interpretation, general relativity entails thinking of the universe as a four-dimensional entity, merging 3 dimensions of space and 1 of time. It's like saying, hey, gravity isn't a mysterious force. It's just how things naturally move in the universe. Within this concept, large objects such as planets, stars, and even humans have an impact on the form of space and time around them. Gravity is our perception of this shaping. Think of space-time as a large, pliable blanket. The blanket is dented when you set something heavy on it, like Earth. Something smaller, like a ball, will roll toward the dent if you set it close to the Earth. This is comparable to how objects behave due to gravity, which is a result of space-time warping rather than an enigmatic force. The motion of planets orbiting the Sun and other objects in our solar system can be satisfactorily explained by general relativity. The orbits of these planets, including Earth's oval orbit around the Sun, may be correctly determined using it. Brian says this isn't the same as the old theory of gravity just pushing everything together, which can't quite explain why planets move the way they do. The new theory, which more closely aligns with observation, holds that space and time are curved like pliable cloth. A solar eclipse in 1919 served as a crucial event that proved general relativity was right. A group led by Sir Arthur Eddington studied the bending of light from distant stars as it approached the Sun. The hypothesis stated that during the eclipse, the starlight would gently curve due to the bulk of the Sun. The validity of the theory was established by the observations aligning with Einstein's predictions. Special relativity states that motion can alter our perception of time, and that gravity also affects time. Time flows more slowly in locations with stronger gravity than it does in less gravitational areas. Therefore, a clock put close to a big object, such as a black hole, would tick more slowly than a clock positioned distant from this potent mass. In general relativity, the concept of black holes, zones of extreme gravity, is introduced. Nothing can escape from a black hole due to the strong gravitational field inside of it, not even light. The event horizon is the border that surrounds a black hole. Once an object passes this barrier, it is drawn into the black hole and does not have a chance to escape. The structure of the cosmos is significantly affected by Einstein's theory of general relativity. He first updated his equations with what is known as a cosmological constant, based on the assumption that the cosmos was static. He called this a major error, though, when we found out it was growing. A fundamental component of the Big Bang theory, which explains how the universe came into being, is the notion of an expanding cosmos based on general relativity. Gravitational waves are a key idea from general relativity. These are rippling effects on space and time produced by extremely massive objects traveling at high speeds, such as mergers between neutron stars and black holes. Another part of Einstein's theory was confirmed in 2015 when researchers at the Laser Interferometer Gravitational Wave Observatory made a direct detection of gravitational waves. Whether by studying how planets move, the bending of starlight, or the detection of gravitational waves, scientists have tested general relativity countless times over the years, and each time the theory has proven to be accurate. Saying that gravity is a lie may seem unexpected, given that we all experience gravity on a daily basis, yet in the field of physics, it is customary to debate and investigate other theories. Scientists like as Brian frequently dispute accepted hypotheses. In the case of gravity, some doubt our traditional understanding of this fundamental force. Modified Newtonian dynamics, MOND, is one theory that contradicts standard gravity theory. It proposes that gravity behaves differently at slow speeds, especially in galaxies, and does not require dark matter. At low speeds, Mond suggests that gravity strengthens rather than adding unseen stuff. The enigmatic theories of dark matter and dark energy, which were proposed to explain specific space-related occurrences, are also at issue in the gravity dispute. Opponents counter that other theories can explain what we see and that these are not necessary. Several scientists who challenge Einstein's theory of gravity investigate novel ideas, such as theories involving unidentified particles or forces that might improve or alter our comprehension of gravity. It's crucial to stress that novel concepts in science are not rejected, but rather put through extensive testing to determine whether they are logical. For example, concepts such as wormholes and shortcuts have been imaginatively addressed alongside Einstein's theory of time and four-dimensional space, where time travel may be constrained by the speed of light. According to Stephen Hawking's chronology protection conjecture, time travel appears implausible from a physics standpoint. Whether these new ideas can explain phenomena like the force of gravity in a way that is consistent with what we already know is the subject of ongoing research and investigations. Though many theories have been proposed, none have been able to logically supersede the established laws of gravity. Science advances by raising questions and refuting accepted theories, which results in additional study and a more comprehensive understanding of the cosmos. General relativity continues to be the most significant and effective theory of gravity. It continuously works well in testing and explains a variety of phenomena, including how planets move and how light bends around enormous objects, in spite of obstacles and competing theories. Due to its simplicity and ability to explain a broad variety of phenomena, general relativity continues to be powerful. According to Einstein's special theory of relativity, time can behave differently depending on your speed, as was previously discussed. Let us now investigate how this concept relates to practical situations, particularly space travel. Because space is so large, and because the speed of light is the fastest object that can travel, space travel is both thrilling and difficult. This is due to Einstein's theory. Because of this, even with modern technology, traveling between stars is extremely difficult because it takes a long time to reach the closest stars. To comprehend what occurs with time when you move in space, think about the well-known twin paradox. Imagine that one twin remains on Earth while the other travels quickly to a far-off star. They discover that less time has passed for them than for their earthly double when the space-traveling sibling returns. This indicates that they have successfully entered the future. For space travelers, time is of the essence since the farther they travel, the slower time becomes. Astronauts may age more slowly than individuals on Earth if they travel to nearby stars, where time slows down considerably. Although it might sound like something out of a science fiction novel, this is a real-world consequence of relativity. Consider the scenario in which humanity dispatched a crew to a nearby star system. Even if they move quickly, the journey could take many years due to the great distance. Due to the time dilation effect, the astronauts on the spaceship would experience a reduction in time, yet on Earth, a significant amount of time would have elapsed. Time dilation affects technology as well as live things. For accuracy and optimal operation, spaceship computers and communication systems need to take time dilation into consideration. Fast spaceflight poses physical difficulties such as prolonged isolation and cosmic radiation exposure in addition to the psychological repercussions of being gone from Earth for a long time. We may see the impacts of time dilation in the Global Positioning System, GPS, in our daily lives. GPS depends on signals from moving satellites arriving at precisely the right time. Time dilation is experienced by these satellites, so these effects must be taken into account for precise GPS computations. Inaction on this part would have a substantial impact on navigation system accuracy. Let's now investigate why time only flows in one way. In the cosmos, time is the supreme ruler, guiding us from the past to the present and beyond. Time travel is a one-way trip that is essential to our life. However, why is time so unidirectional? We examine entropy, a notion that quantifies disorder or unpredictability in a system, in order to gain an understanding. Time tends to flow in one direction due to entropy, which is related to the time arrow, and tends to increase throughout time. This relationship is expressed by the second law of thermodynamics, which states that total entropy will either rise or, at most, remain constant in any isolated system. Put simply, entropy does not naturally tend to decrease. Rather, it naturally tends to grow.